I'll try to explain the physical meaning of these three mathematical tools, which are used across various fields of physics. We know that this is a scalar, so just a number, and this is a vector, a number or a magnitude with a direction. Now, this is called a scalar field because multiple scalars are present. And this is called a vector field because multiple vectors are present. So a field is formed when we have a bunch of them distributed in space. So, where are these concepts used? As one example, a scalar field can represent geographic altitude, where it assigns an altitude value to each point in space. Scalar fields can be mathematically expressed using scalar functions. So for any given x and y coordinates, you'll obtain a value that represents the magnitude at that point. A vector field can represent wind directions, and of course this can be expressed using vector functions. And we can also express this as a matrix like that at the bottom. So I'm gonna use F for the scalar field and V for the vector field. Okay, now today's topic. What is this downward pointing triangle? This is called a del operator, which performs partial derivatives. As you can see, del operator is a vector type, which means we can also express it as a matrix, like that. Let's see what each operation represents. Alright, first let's see what happens when we apply the del to a scalar function or a scalar field. This process is called gradient. So the gradient of a scalar field. I brought a function here just as an example. Let's take the gradient. The scalar field becomes a vector field. Now we have directions. Obviously, since the del operator performs a partial derivative in each direction. Let's remember this. The gradient of a scalar field gives a vector field. Okay, so 2x in the x direction and 2y in the y direction. And what is this telling us? This is how the function looks on a graph. I'm going to show you what this gradient of the function tells us. We need a top view of this graph. I'm just going to choose a random point, 5, 10. Plug the values into the vector field. We get 10, 20. By the way, don't confuse. 5, 10 was a coordinate, and 10, 20 is a vector, not a point. Now, this vector means the point should move 10 units to the right and then 20 units up. So I'm gonna draw an arrow like this. Let's look at another random point, 5, 5. At this point, we obtain this vector, telling us to move 10 units to the right and 10 units up. Let's look at another one. It seems the vectors are heading outward from the pit. Shall we try with a point slightly away from the center? Maybe this one, 10, 0. We get the vector 20, 0. It seems to be heading in the same direction as the blue one, but faster. You see how this pit becomes steeper as you move outward? Yeah, it's related to that. These arrows are too large, so I'll just resize them and also show all the other vectors. Look at this. It seems like all the arrows are pointing toward the higher regions, the higher scalar values. I've brought some other scalar fields. You see all the vector fields shown with arrows are pointing toward higher regions. I kinda like this one, so I'll make a conclusion with this one. So when we're given a scalar field, the gradient of that scalar field shows all the trends toward the higher scalar values. It's like if we want to create this hill, we need to gather sand in this direction, right? Okay, so that's what the del operator does to scalar fields. It gives us this kind of information. Let's now see what it does to vector functions. But wait, we can't apply the del operator like this. Del operator is a vector, and so is v. If the two are both vectors, how could we combine them? We could use dot product. This process is called divergence. When del is applied to f, it's called the gradient of f, right? When it's applied to v, it's called the divergence of v. We can never have a gradient of v. So divergence of a vector field. The word diverge means spread, right? In fact, the divergence of v tells us about the spreading. I've brought some vector functions, vector fields, as examples. Like I said, the divergence is just a dot product, and I'll assume you know how to do the dot product. If you don't know, dot product is just one way to multiply two vectors. And if you want to learn more about it, I'll put a link here in the corner. Okay, so the divergence of the first vector field gives 4. The second one gives -4. So this makes sense. The first one is spreading out, so it is diverging, so positive value. But the second one is converging, which is the opposite of diverging, so the negative value makes sense. So the divergence of a vector field does tell us about spreading. By the way, if you have studied electromagnetism, the divergence is in fact used in one of the Maxwell's equations, where we have the charge density here. So if the charge density is positive, the divergence is positive, means the electric field is spreading. If the charge density is negative, the divergence is negative, means the electric field is converging. Didn't you notice anything? This is why the electric field of a positive charge spreads out, while the electric field of a negative charge converges in. Because positive charge means positive number, and negative charge means negative number. Huh, interesting, eh? Everything makes sense. Every definition has its reasons. Anyway, let's move on to the third graph. The divergence is 0 this time, which means the diverging isn't happening. It sounds correct, since the arrows look consistent. This field definitely doesn't show any spreading, right? Now, this last one is important. Even if the arrows are not spreading apart from each other, change in their size could still indicate divergence. Not all the time, the divergence could be just 0. Alright, at this point, you might start to feel that the term spreading doesn't precisely capture the concept of divergence. So, is there a better term or a better explanation we could use instead? Don't worry, there is. Change in density. To talk about density, we need to define a unit region. In polar coordinates, this would be a circular unit region. In Cartesian coordinates, it would be a square unit region. Keep in mind, we shouldn't have ellipses or rectangles. Since we're working with unit regions, unit means the fundamental size, right? The region should be symmetric across all dimensions. Like, we don't use a graph with uneven grid sizes, right? Okay, so since our vector functions are all in Cartesian, why don't we use the square one? Sounds good? Okay, so let's go back to the first graph and try to understand again what divergence tells us by looking at changes in density. I know I haven't written the divergence of the last one, but we'll come back to here later, okay? Let's pick a random region in the first graph. Why don't we just start from the center, okay? Now, imagine we have a fluid of particles. It seems there are 16 particles inside the square region at the moment. Now the vectors will make the particles move. Watch. What happened to the density in that region? The density has decreased. A decrease in density means spreading, right? Indicating positive divergence. And if we look at another region, we'll notice that the density decreases there as well. Surprisingly, this particular vector field shows a constant divergence of +4 throughout the entire space. Okay, what about the second graph? The density increased. The fluid is compressed rather than being stretched. The divergence is negative. And the amount of divergence seems to be constant in here as well, -4. Okay, now the third graph, let the particles flow. No change in density, so no divergence. Makes sense. Now the last one that was ambiguous to us. I'm gonna write the divergence now. The divergence is 2x, which means the amount of divergence could change depending on where we are looking. For example, let's center our region to 8, 0. Then the divergence is gonna be plus 16, meaning it is diverging because it's positive. The density is decreasing, meaning it is diverging. Makes sense, because you see, the particles are exiting faster than the ones that are entering. So in overall, it should decrease. If we center our region to negative 8, 0, the divergence is going to be negative 16, right? So negative divergence means increasing density. And you see here, more particles are entering than exiting, so makes sense. What about the center? The divergence is 0, and this also makes sense, since the amount that are entering and exiting are the same. So, thinking about the change in density makes it much easier to understand the divergence now. Do you agree? And lastly, we shouldn't forget this. Plus 4, negative 4, 0, 2x. We've only gotten scalar numbers, right? Divergence of a vector field always gives a scalar field. And this is just a dot product, so we should get scalars, of course. Shall we move on to the third topic now? As you probably know, there are two ways to multiply two vector types, the dot product and the cross product. The dot product compares the two vectors along the same line using cosine, which is why this was about the divergence. The cross product measures how much one vector rotates the other using sine. And this is why the third operation is called curl. And another difference is that the divergence gives a scalar field, the curl gives a vector field. It has directions. Again, I'll assume you know how to do the cross product. I'll put a link for the cross product too. Okay, so if you take the cross product, you'll see that all of them give 0. We can already kind of tell, since the fields don't seem to rotate. You agree, right? Okay, so let me bring a new vector function as a good example. This vector field curls. Let's check this one. So, if we take the curl of this vector function, we get sine y plus cos x in the z direction. Okay, so the answers again depend on the coordinates. Let's have a look. Let me pick this point, 0, pi over 2. If we plug in the x and y values, we end up getting plus 2 in the z direction. For better understanding, here's the side view of the graph. Plus 2 in the z direction is this. And you see how the arrows are rotating in the counterclockwise direction around that point? This is precisely the right-hand rule from physics. Isn't this cool? Positive curl means counterclockwise rotation. Let's look at another point. How about pi, negative pi over 2? This time, we'll get negative 2 in the z direction. Negative means downward on the graph. And this is also true using the right-hand rule. The vectors are in fact rotating in the clockwise direction, right? Around that point. And lastly, let's look at negative pi over 2, 0. You'll get 0, meaning no rotation is happening. And so it seems. They're not rotating, right? So the curl gives us this kind of information. And again, the curl of a vector field always gives a vector field, since this is simply the cross product. Alright, so let's summarize. Gradient of a scalar gives a vector which shows trends toward higher scalar values. Divergence of a vector gives a scalar which tells whether the vector field diverges or not, and we studied this by looking at the changes in density. And curl of a vector gives a vector which tells whether the vector field curls or not. If the answer is pointing upward, it means counterclockwise rotation. If it's pointing downward, then it's clockwise rotation. I'm telling you, these are very useful mathematical tools to understand fields in physics. I hope this video was helpful, and don't forget to press like and subscribe to our channel. It really motivates me.